Okay, so the last part of chapter 5.1 is going to be to talk about a couple of more complicated cases. The first, what happens when f and g change places. The second, what happens when we have to work with, say, a horizontally oriented rectangle instead of a vertically oriented one. So it's going to be easiest to motivate the first section by starting with a picture. So if you had curves that were sort of, say, periodic, this is an easy picture to draw. Suppose you had one curve that behaved like this, and another curve opposite that looked like this. And you wanted to figure out the area between these two curves. Well, let's suppose that you had x equals a and x is equal to b. And the question is, what is the area contained in the region between them? Well, the region between them now, which looks like this, the issue is that you have different rectangles, different typical rectangles. So if you draw a rectangle in this region and try to use that to form a formula, then what you're going to find, suppose we call this f of x and this g of x, what you're going to find is that the area of this typical rectangle here is going to be a is equal to f of x minus g of x delta x, because f is the function that's on top. The second part of the region, the height of that rectangle is not f minus g, it's g minus f, because g has now become the function on top. So the area of that rectangle is g of x minus f of x delta x. So there's not going to be a consistent way of writing this formula down without taking that into account. Okay? So it turns out to be that the solution to this is to chop each one of these regions into its own integral, because I can only write down an integral formula that can be computed with if the rectangles are consistently determined. Okay? So again, to reiterate, what I'm saying here is that this rectangle, if you look at the top and you look at the bottom, f is on top of this one. So the height of this rectangle is f minus g. The height of this rectangle is g minus f. Okay? Okay, so what are we going to do? We're going to need three separate integrals. And that means I have to have endpoints and top and bottom curves for each one of these three regions. So let's just suppose, for the sake of argument, that this was x is equal to a, and this is x is equal to b, and this is x is equal to c, and this is x is equal to d. Then using the formula, now I've got individually considered, this region looks exactly like what we did before, where one curve is always on top and one curve is always on bottom. So the area of that first piece is going to be the integral from a to b of f minus g dx. The second region, again, g is always on top and f is always on bottom. So this is going to be the integral from b to c of g minus f dx. And for the third region, f is back on top. So its area is going to be the integral from c to d of f minus g dx. And the area of the whole thing is the area of the three pieces added together. Okay? So again, what we're doing here is, this region, I just used the same formula I had before because f is always on top. This region, I use the same formula from before, but g is always on top, so it's g minus f to determine the height of the rectangles. And for this region, f is on top, so it's f minus g to determine the height of the rectangles. Okay? And so the sum of areas gives you the area of the entire region. There's a shorthand that you can use to write this down. You notice that on the interior of each of these integrals, we have either f minus g or g minus f. So it turns out to be the case that the shorthand here is, I can write this as the integral from a to b of the absolute value of f minus g dx. So the absolute value generally is not a function that you can integrate. Absolute values always indicate formulas that need to be broken up into pieces depending on if what's inside the absolute value is positive or negative, because the absolute value is actually a piecewise defined function. So you can't actually use regular old integration formulas on this because it doesn't really have an antiderivative. Its pieces have antiderivatives, but the function itself does not. Okay. So That's the approach that we're going to take when we're looking at places where curves cross over each other. Now, if we're given that situation, it's incumbent on us to figure out where those breaks happen and where the functions that we're thinking about change places. So we have to figure out where that happens. Okay, so let's actually look at an example and see if we can apply this in action here. So this is example 3. And so we're going to be looking at the area between y equals sine x, y is equal to the cosine of x is equal to 0, and x is equal to pi over 2. Again, start by drawing a picture. Okay? These problems are much more difficult without pictures. So the cosine function starts at 0, 1, and at pi over 2 it's equal to 0. So here's cosine. So this is y equals cosine of x. The sine function starts at 0, and at pi over 2 it's equal to 1. So it looks like this. Now I can already tell I'm going to have two integrals here because the first part of the region has the cosine on top and the second part has the sine on top. So this is the region that we're interested in finding the area of. Okay? I know I need two rectangles, and what's going to cause the split, or two regions. I know I need two regions, and what's going to cause the split in the regions is going to be this point of intersection between the two curves. So this is the breakpoint between the two regions that I need to work with. So that means I need to know where that breakpoint is. So just like before, I'm going to say, well, where is the sine of x equal to the cosine of x? Of course, the answer is infinitely many places, but because I'm restricting my attention to just the numbers between 0 and pi over 2, there's only one point where that happens between 0 and pi over 2. So sine and cosine are equal to each other at pi over 4 if we're on the interval from 0 to pi over 2. And what that means is that we should expect that what we're going to have is an integral from 0 to pi over 4 of some stuff, plus an integral from pi over 4 to pi over 2 of some other stuff. And so we can actually just write down what those integrals are based on which function is on top and which function is on bottom. So considered separately, I can write down integrals for these two regions just by looking, as before, at a typical rectangle. So the typical rectangle here looks like this. Its area is equal to the cosine of x minus the sine of x times an increment in the x direction. The typical rectangle for the region 2 has the sine on top and the cosine on bottom, and so its area is going to be the sine of x minus the cosine of x times an increment in x. Okay, so that right there is enough for me to write down the two integrals that I need. So again, without following a formula, I can intuit my way through what the formula must be. I could have written this down as an absolute value expression and then figured out the piecewise definition of the integrand based on where the breakpoint was. That is where the functions switch places. But this graphical approach, I think, is a lot clearer in what's going on. So the area of the first region between the curves, so that's this region right here, that should be equal to, so we'll call that A1 and this A2. So A1 is equal to the integral from 0 to pi over 4 of the cosine of x minus the sine of x dx. And the second region has area given by the integral from pi over 4 to pi over 2 of the sine of x minus the cosine of x dx. What will happen if you neglect to use the absolute value, if you just used, say, cosine of x on top and sine of x on bottom for the entire integrand, you would end up with an area of 0, because these two regions are of equal size, but the top and the bottom flip places. So if you don't use the absolute values to switch the sine and cosine from negative to positive, it actually just, the way that the integral is computing is it would be thinking, okay, well, the rectangle is turned upside down, and so when they turn upside down, that must be negative area. Okay, so it's important to break this into regions or to think about in terms of the absolute value. Okay, so now it's just a question of computing some integrals. So the area is going to be equal to the integral from 0 to pi over 4 of the cosine of x minus the sine of x dx plus the integral from pi over 4 to pi over 2 of the sine of x minus the cosine of x dx. These are more table integrals that you're just supposed to know. Be careful with signs when you do these things. I mess these up too. So what you're going to get out of this is going to be, well, the integral of the cosine is the sine. And the integral of the sine is the negative cosine, but this is already negative, so it's positive cos x. And this is evaluated from 0 to pi over 4. The integral of the sine is minus the cosine. The integral of minus the cosine is the sine, but there's a negative in front, so it stays negative. And this is evaluated from pi over 4 to pi over 2. All right, so at this point, we're ready to just plug the numbers in and do some calculations. I would strongly suggest that if you don't have your unit circle memorized, that you go back and think about the unit circle angles and their sines, cosines, and tangents, because most of the examples that are of interest in calculus are trigonometric. Okay, so it's important that you be able to do these quickly. So the sine of pi over 4 is root 2 over 2, and the cosine of pi over 4 is root 2 over 2. The sine of 0 is 0. Cosine of 0 is 1. Then we'll do the same for the right-hand side. So the cosine of pi over 2 is 0. The sine of pi over 2 is 1. Then we get minus root 2 over 2 and minus root 2 over 2. And when the dust clears, you end up with 2 root 2 minus 2 as the final answer to the question. Okay? Okay, so now I want to talk about what happens when we have rectangles that are horizontal and what the setup is for that situation. So instead of giving you a redo of the theory, instead what I'm going to do is I'm going to write down a specific example, and then we're going to work through how we must write that down. Okay, so we're not going to rely on a formula, although there is one in the text. We're going to try to figure out from the picture what the formula must be by building and using our calculus intuition. So the particular region that I want to work on is y is equal to x minus 1, y squared is equal to 2x plus 6, and that's all the information we're given. So we know we're going to be working with points of intersection here as well. So as before, I'm going to start with a plot. Okay, so the curve y equals x minus 1 is a line that looks like this. It has slope 1. It has y-intercept negative 1. So there's y is equal to x minus 1. The parabola y squared is equal to 2x plus 6 turns out to look like this. Okay, so you know that it's rightward opening because the y value is positive. This is the setup for the picture. And the region that I'm interested in trying to find here, I haven't even drawn, is the area between them, which looks like this. So the first question is, why wouldn't you want to use vertical rectangles on this problem? And the answer is, if you did that, you'd have to use two integrals because the definition of the rectangles would change. And worse than that, the same curve would be the top and bottom of the rectangles in one of those regions. So what do I mean? I mean, let's just suppose that naively you thought, I am going to try to work with the regular old dx formula. So I'm going to draw a representative rectangle. The first rectangle that you drew would be in this region right here. So if you drew a rectangle right here, the issue is the same curve is the top and the bottom. Okay, now that's a problem. Then when you were over in this region, the rectangles would look like this, and now there'd be a different definition because now the pink curve is on top and the blue curve is on the bottom. That means that there's no way to avoid doing two integrals here, and one of the integrals is going to be really nasty. The correct way to approach this problem is to work horizontally. And what I mean by that is we want our typical rectangles to look like this. Because if we write a typical rectangle down in this direction, then the same curve is always on the right, the same curve is always on the left, and as I go up and down the region, the rectangles don't change their orientation. So what I want to say here is to compute the area of this rectangle. Well, it's skinny, but now it's skinny in the y direction. So this particular rectangle is delta y thick. Well, delta y tells you that it must be a y integral. So we're going to be working in the y variable. As soon as you have an integral that's going to involve y's, the variables have to be y's, which means that you have to work with functions of y, which means you have to solve for x. So x as a function of y. So I know I'm going to be working with a y integral. I want to rewrite the definitions of these curves. This is what y squared is equal to 2x minus 6. I want to rewrite the definitions of these curves so that they are x as a function of y. So the blue one is pretty easy because x is equal to y plus 1 is x as a function of y. And the red curve is pretty easy too. I think you get x is equal to 1/2 of a y squared minus 3. Okay? So the rightmost curve is given by x is equal to y plus 1, and the leftmost curve is given by x is equal to 1/2 y squared minus 3. I need the y variables because I'm going to be integrating with respect to y. Okay, so let's write down what we're actually going to do. So I have my parabola, and I've got my curve. And algebraically, I know that this value here and this value here I'm going to need in order to integrate. Okay, so let's actually do that real quick. So now that I know that my x values are equal, so remember my two curves were x is equal to 1/2 y squared minus 3, and x was equal to y plus 1. If I set those two values equal, 1/2 y squared minus 3 is equal to y plus 1. So I can clear denominators by multiplying by 2, which will give me y squared minus 6 is equal to 2y plus 2. If you sort that all out on one side of the equation, you get y squared minus 2y minus 8 is equal to 0, which factors as y minus 4 and y plus 2. And so that means our points of intersection here are y is equal to 4 and y is equal to minus 2. So these are our limits of integration. Now the reason that we're working with y values here is because if we're working with rectangles that are chopped up this way, we need to start thinking, okay, well I'm going to start adding rectangles at y equals -2 and then chop, 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 one chop for each value of y until we get to the final y value, which is up here at y is equal to 4. Okay. So now we're ready to actually write down what the integral must be before we do the computation. Just writing the integral down is an assertion that you understand what's going on in a problem, okay? Because remember, a definite integral is an area even if you haven't computed it yet, okay? It's a representation of the area computation. It's a number. So I know that the rightmost curve of my rectangles is given by x is equal to y plus 1. And the leftmost curve of my rectangles was supposed to be x is equal to 1/2 y squared minus 3. And so that means that the integral must be, well, I start cutting at -2 and I finish at 4. My rightmost curve is y plus 1. I subtract off my leftmost curve to get the height of the rectangle, 1/2 y squared minus 3. And then the skinny direction of the rectangle, the width of the rectangle, is given by dy. So even from here, you should be able to always take the integral that you write down and interpret it from the picture that it came from. So the -2 and the 4 come from the limits of integration, -2 and 4. the y plus 1 and the 1/2 y squared minus 3, those tell you the width of each one of these rectangles from the rightmost curve to the leftmost. And the dy tells you that these are skinny rectangles in this direction. Chop, 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 chop. Okay? So the last step is just to write down what the integral is. So a is equal to the integral from -2 to 4 of y plus 1 minus 1/2 y squared minus 3 dy. So at y minus 1/2 y squared plus 4 dy. And then if you grind through the computation with the power rule, you should just end up with the answer 18. So this is a check yourself. Okay, so that's the basic theory of working on the area between two curves. And the approach that we took here of taking the region that we're interested in and cutting it up into rectangles and trying to figure out the formula from the rectangles instead of consulting a formula and just plugging functions in, is the intuition of doing this is going to underlie all of the three-dimensional stuff that's coming in the next chapter. So as we start moving into 3 dimensions, this idea of figuring out which direction we're chopping, what the area of the pieces that we're chopping up into is going to be how we approach taking volumes and cutting them up into pieces and computing their approximations or integrals as well. So I would strongly encourage that the process you use for computing these things is always the same, which is start by writing a picture, take the problem, plot the graphs, write the picture down. From the picture, you should be able to figure out how many pieces you should be looking at, how many integrals there are going to be, as well as what the orientation of the rectangles should be. Once you have that done, then you can find any points of intersection if you need them. If the curves cross each other and you weren't given that information, you can find that. Then you can write the integrals down. Once you have the integrals written down, you should be able to look at the integral and interpret the region that it came from, right? The integral is not just a random pile of numbers and functions. It's a meaningful representation of the area that was written in the graph that you made. The most valuable skill you're going to take away from it is the intuition and building that you're doing when you're modeling the problem with a picture and a process. All right, see you next chapter.